Start. All right. Our last class we did the Galerkin formulation, so we're going to do a quick recap. If you remember, we talked a lot about this energy space, and we said that we were dealing with functions that give you finite strain energy, and that makes a lot of sense in mechanics. There is nothing that has infinite strain. Things break apart, okay? And so we call that E. We look at the Galerkin formulation, and the idea of the Galerkin formulation is, okay, we cannot really work in an infinite dimensional space. It doesn't make sense. We cannot put a problem that has infinite dimensionality in a computer. We just have a finite set of resources, and so we kind of need to find a solution in a subspace of that energy space, right? And so we constrain our solution to a finite dimensional space, and that is basically the essence of the Galerkin projection. How do we go from an infinite dimensional space to a finite dimensional space, right? And so what the idea, just to what is this infinite dimensional space? Just to wrap our heads around this abstract idea, we look at the definition of a function, right? So say this u of x. Well, if I can represent this function as an infinite product of coefficients or degrees of freedom and basis functions, this function can pretty much represent any function, right? And so this is to me an infinite dimensional representation of what that space would be, right? Okay, but as we said, we're going to relax that requirement, and we said that we're going to look for a subspace, and that this is basically contained in that infinite dimensional space, and by doing so, we reduce the dimensionality drastically to something that we can actually manage. We can fit into a computer, we can code that, and we can get a solution, or an approximation to our problem, right? And while doing so, we accept that there is going to be an error. So we know there will be an error in most cases, right? We said you can get the solutions, the exact solutions to a problem in 1D very, very easily, but the moment you go to 2D, 3D, finding the exact solution of a problem is mission impossible, right? It's not going to happen in most cases, unless, of course, there are some particular problems that have been widely studied in the literature, like you have square plates or circular plates, and very easy boundary conditions and things like that, and those have been studied thoroughly. Okay, so we looked at this idea of the orthogonality of the error, right? Just to try to understand what the Galerkin projection is actually doing. And if you remember, to me, right, and this is my personal opinion, the Galerkin projection is the best thing ever invented in mechanics. The idea, right, that you go from an infinite dimensional space to a finite dimensional space, and you get the solution of a problem, and it so happens that finite dimensional solution is the best solution possible chosen from that set of functions that you're working with. This is, to me, mind-blowing, okay? And we kind of, the math is super straightforward, right? So you start with the statement of equilibrium in abstract form, right? This is, again, the infinite dimensional space. And we said, well, if it works for the infinite dimensional, of course it works for a subset. So now I go from E to EH. Remember, the moment we talk about EH, we are already in a finite dimensional space, right? And then we basically wrote now, instead of U, we use UH. So now we are indeed dealing with the trial solution, right? And if you subtract these two, you see that now the bilinear form, in the bilinear form, we have this error. Remember the properties of the bilinear operator. This minus this is going to be basically this guy here. And the right-hand side is exactly the same. So again, when we look at this expression, this is saying that the error, right, if I take a look at the error of the approximation, which is U minus UH, right, when I account that for W, so for all the functions in that W, in that EH space, well, this inner product between those two functions, the error and WH, in the sense of the bilinear form is equal to 0, right? And so we try to understand what this meant, right? Like, it's basically an inner product of functions. On the one hand, we have the error in the approximation. On the other hand, we have all the functions in that EH space. And somehow we're saying that this inner product is equal to 0 in the sense of the bilinear form, in which case, in the sense of the bilinear form, these two are orthogonal. So somehow, right, this Galerkin projection is picking a function such that the error remains orthogonal to the entire space, which is crazy. It's crazy. Why is crazy? Well, because we know that from all those functions in EH, we're picking the function that best approximates the exact solution. And we did we tried to interpret this in different ways. And we said, well, the error U minus UH is indeed orthogonal to the subspace. We said that, in other words, the UH is basically the projection, right? If we look in terms of Euclidean spaces analogy, remember, this is an analogy because, of course, we are dealing with function spaces, not with Euclidean spaces, right? The projection into that space is basically, so UH is the projection of U into that space. And then you can actually prove this mathematically, and this is done in the book with Sia's approximation theorem. You can actually prove that your approximation is the one that indeed minimizes the error, and the proof is, again, very simple. Okay, but that is the Galerkin projection. And you may argue, well, the Galerkin projection uses EH, and EH could be anything that is finite dimensional, yes? Okay, but now we are going to get into the realm of finite elements, because for the first time in this course, we're going to look at finite element spaces, okay? And this is the objective of today's lecture, so we're going to start with the finite element discrete equations. Because, of course, the objective is we need to figure out how we are going to put all this information that we learn into a computer to solve for the boundary value problem that we have, okay? All right. So let me quickly draw here a representation of a mesh. So 1, 2, 3, 4, 5. So this is going to be our bar. So again, we are going to represent this as omega h. That is, again, as a subset of the reals. Remember that this is the way we define our domain. And notice that I use omega h now. So now we are indeed in a discretized setting. Okay. So this is going to be my element 1, element 2, element 3, element 4, element 5. And, well, accordingly, you could argue that this here is going to be my node 1, 2, 3, 4, 5, 6. And so if I want to plot what are the functions that we're going to be using, and let me just, for instance, maybe I delete this a bit. Like this. And if I say this is going to be equal to 1, well, let's try to write some functions. Let's say that the first function is like this, and I'm going to call this phi1. And I take this one, and I'm going to call this phi2, and I take this one, and I call that phi3. And let me go to this one. Phi4. And I'm running out of colors. Let me go to that one. Phi5. And let me get to that one. Phi6. Well, these functions here are the so-called roof functions or hat functions. They look like a roof, right? So these are piecewise linear polynomials, right? And there is an expression that you can use to create them. So phi I is going to be basically x minus xi divided by xi minus xi minus 1 for x in the interval xi minus 1 and xi, and then xi plus 1 minus x divided by xi plus 1 minus xi for the interval xi plus 1. So these functions have a really nice couple of properties, right? The first one is that they satisfy the so-called Kronecker delta property, and if you remember, we talked a little bit about this in the nonlinear mechanics class, right? We said, what is it? Someone remembers what is the Kronecker delta property? Yeah.
Condition unity?
No.
It has to do something with matrices that if the row and the column equal each other, the output is 1, and if they don't, then
Yes, kind of, yeah, more or less that is the definition. So in essence, the Kronecker delta property is phi I evaluated at xj is equal to delta ij, right? This is the Kronecker delta property. And so this means basically that if I take this function phi I, if x is equal to xi, so then you have delta ii, which is equal to 1, right? Now, if x is equal to j, so then this is delta ij is equal to 0. That means that, as you can see in this figure, right, all these functions are equal to 1 at the location of their corresponding node, and they are equal to 0 at the location of every other node. So that is a so-called Kronecker delta property. It's a nice property to have. And it's a nice property for many reasons. First, and we will see this later, the physical meaning that is assigned to the degree of freedom is that of the actual field. Of, let's say you're computing the displacement, so now you compute the solution to the problem. Now the coefficient or the degree of freedom, right? That has the physical meaning of the displacement at that location. That is one of the things that is a natural outcome from this Kronecker delta property. Because let's say if the function at the location of a node is not equal to 1, then, well, you need to evaluate what would be the actual physical quantity there, the field, the displacement, okay? All right, and indeed, someone mentioned partition of unity. Indeed, these functions form a partition of unity, which means that if you sum all of these functions in the domain, it's equal to 1, right? So we can say that the sum of phi I of x is equal to 1 in the whole domain, and this is the so-called partition of unity. That, for the purpose of this course, is not so important. The moment we go to more advanced formulations like generalized finite element methods, extended finite element methods, this is actually a very important property to have, because they lead to the so-called reproducibility condition, but we are not going to meddle with any of that in this course, okay? All right, so now that we have discretized our domain and we have our functions, right, we're going to take the trial solution and the test function from this finite element space. So we take UH of x to be, well, the sum equal 1 to 6. Keep in mind that I have only 6 functions, UI, right? Notice that now here, my UI is the actual coefficient that I use, the degree of freedom, and then, of course, these are just scalars, right? They are coefficients that are multiplying our basis functions, our shape functions. In finite element terminology, these basis functions are called shape functions, okay? Okay, well, and if we're going to go for this Bubnov-Galerkin approximation, if you remember, what was the Bubnov-Galerkin? we're going to take the test functions to be, yeah, but same space. So we're going to take our test function wh of x is going to be equal sum I equals 1 to 6 phi I of x. That doesn't change, and now I have these coefficients wh. And well, by taking those two, we can formulate now our finite dimensional form of equilibrium that again we can express in abstract form, right? Find UH in that space that we called EH of omega H, such that, well, again, the bilinear form is equal to the linear form for all test functions in that, let me put this back here, for all WH in EH of omega H. Okay. Well, let's plug in those expressions. So we have now the bilinear form, right? And I have here, remember that the bilinear form was commutative. It didn't matter whether UH or WH was on one hand or the other. So you could actually write this expression as J is equal to 1, 6, phi J, WJ, comma, sum I is equal to 1, 6, phi I, UI is equal to L, and again, sum 1 to 6, and this now becomes for all WI's that belongs to the real, and of course I goes from 1 all the way to 6. So it's just to say that now all of those are coefficients. Yeah.
Is there a reason why you switch U and W?
Yeah, and this will become more apparent later when we do the matrix form, because I like to get to the discrete equations in two different ways, and you will see in a minute why. Yeah.
And from the first line to the second line, essentially the degrees of freedom of the test function, all the other degrees of freedom have just dropped out.
Not yet. We have not dropped yet, and we will see that in a minute. Okay. So of course coefficients we can take them aside, right? So now I have basically here, because the coefficients are constants in the sense of the bilinear form. Remember, it was an integral. Everything that is constant, that is a coefficient, we can take it to the other side. Because indeed it has to be the same. Okay.
Then you're going to distribute it.
So what I'm going to do is now you have these guys. Of course, the 6 are there. And then we have the sum, WJ. And then we have and then this is still valid for all WI in R. And I, keep in mind that this is no longer I, but it's actually J. And then when we take all of these coefficients out, right, we're going to copy this guy. And now we're going to group terms to the left-hand side. We have minus L phi of I. this whole thing is going to be equal to 0. And again, this is valid for all wj in R. J is equal to 1, 6. And now if you see, because this expression here has to be valid for all coefficients, right? You could argue, say, well, then this whole thing has to be equal to 0 for this whole expression to be equal to 0, because the wj's here could be anything. And I messed up this thing again. It's j. Right? So this here is going to lead, this term here is going to lead what we are going to have as our stiffness matrix. This guy here is going to be our displacement vector or degree of freedom vector. And this one here is going to lead to the so-called force vector. And so the whole discretized problem is going to turn into ku equals to f, which of course we solve for u. Yeah?
Why did the linear problem go to phi j to phi y in the final form?
Sorry?
You have with the linear you have phi j, and then
Yeah.
and phi.
Yeah. You mean this guy?
Yes.
Yeah.
But shouldn't it just be phi y actually? Because I'm confused why that is actually phi j.
Well, because those are the ones for the weight function. So everything that is weight function should be j. Everything that is trial function should be I. Yeah. Remember that the test function shows up on the both the bilinear form and the linear form, right? And so it has to be the same function, right? And you have to be consistent again, because again this is going to take you to 6 equations, right? That's why I'm saying that this expression here has to be valid for j equals 1 to 6. So it's basically 6 equations. When you look at it, then it's going to be something that eventually can be set in matrix form, right? Where you have the product of k u equals to f, and that k u is basically k I j u j is equal to ui. So that is so the indices have to end up matching that description.
So phi is the row number of the stiffness matrix, and I is the column.
So j is the row
Yeah.
number, and I is a yeah.
But didn't you switch it up then? Because when I look at the third row from above, you have the weighted function u phi y, not phi.
Sorry, switch where?
At the how do you say this? The third row from above, you have
This row?
Yeah, that row.
Yeah.
Then the second term, the weighted function is phi y, not phi j. Or am I wrong now?
So this guy here is our trial solution. This here is our test function, and the test function is popping up on the other side again. It's just that here I'm using j as the index for the test function, right? And I'm using I for the trial solution. But then when you go to the matrix form, they are inverted, right? It's ij. So this expression here is kij uj is equal to fi. Because this is normally the way we write equations, right? Like in matrix form. So you notice that these are actually inverted from the convention that I took to derive this. So I assigned the j to the test function and the I to the trial function, but this is arbitrary, right? Okay. Okay, but what I want to show you very quickly is that indeed, from an infinite dimensional space, by choosing these two functions from this finite dimensional set and plugging them in, right? Then, of course, you pick a j, and then you have one equation that needs to be satisfied. So that has to be satisfied for all those coefficients, right? That goes from 1 to 6. And again, we have a dimensional problem of which size?
And the number of nodes.
Which is?
N.
We have how many nodes?
6.
6 nodes. So we have a 6-dimensional space. We have 6 equations to solve. So that already gives you an idea on the fact that now that we're dealing with finite dimensional spaces, and in particular finite element spaces, right? Your system, at least in 1D, is going to have the dimension of the number of nodes. Of course, that is going to change whenever we go, for instance, to 2D, and we're dealing with the structural problems. Now, how many degrees of freedom per node you are going to have? 2. And so, what would be the size of a system that we need to solve in 2D?
Square.
Yeah, twice the number of nodes. And if you go to 3D, 3 times the number of nodes. So now you have an idea that in the finite element world, right, whenever you discretize your system, you are going to get a size of your matrix to solve that is indeed proportional to the number of nodes in the mesh. And what is that proportionality constant? Well, it depends on the dimensionality. And I'm talking about structural problems, right? If we go to a heat conduction problem, it's different, because what is the number of degrees of freedom for a heat conduction problem in 2D? The number of degrees of freedom per node. 1 is just a scalar field, it's a temperature. So it doesn't matter if you have a 1 or 2 or a 3-dimensional problem in heat conduction, you're always going to have a size of your system that is going to be equal to the number of nodes. Okay, but of course this is like the in a way the mathematical approach to get the discrete equations, right? It's very simple. You have the bilinear form, you plug them. It wasn't very simple with the index. But we just have to be consistent, right? Like as long as this guy is the test function and this guy is the test function, and we keep the indices in check and they are the same, and indeed I made a mistake in the beginning and these were switched. As long as we do that, we end up having a system of linear equations to solve. So you see again that the discretization process, the moment we choose a finite dimensional space, is going to lead a discrete system of equations that we need to solve. And we need to solve for u. And how do we solve that? Sorry? Yeah, we have to invert, but normally in this world we don't invert a matrix, because inverting a matrix is actually very, very expensive. So we do factorization, right? We do LU factorization or Gaussian elimination. Yeah.
I was wondering where exactly does discretization happen, because I was just thinking that.
Yeah.
Okay, the Galerkin projection in a way does discretize from an infinite space to a discrete number space.
Here.
Equaling the nodes.
That's where discretization happens. Now we go from this, which is infinite dimensional, and now we take a finite dimensional representation of that function that has only 6 coefficients.
And where exactly do the degrees of freedom drop for the test function?
Well, right here, because we are saying since this equation, this whole equation has to be equal to 0 for all coefficients, the only way that can happen, of course, assuming that we don't have a trivial solution for which this Wj is equal to 0, the only way that can happen is by making all of these equal to 0 only. Yeah?
Is the Galerkin projection then not discretized, or is it discretized?
The Galerkin projection here,
Yes.
it's already discretized. Yeah? So this is just to show the orthogonality of the Galerkin error, but now we are indeed in the projection. So we are looking at this UH, which is already not the exact solution anymore because we're in a finite dimensional space, and we call that, how do we call that? That we are no longer in an infinite dimensional space. We call UH our?
Mesh.
No, this function is this guy. Our trial solution, okay? Our trial solution, okay. But as I said, there is a different way to obtain these equations that I also like very much because in a way it has a more mechanics feeling, right? So what we're going to do now, we're going to look at the equilibrium at a single element, right? And we're going to see how that works. Okay, so consider the equilibrium of one element. And say we take this this is my EI, this is XI, this is XJ. And now we're going to write what is the weak form of equilibrium from that element. And we're not going to write in the abstract form, but we're actually going to write what is the actual representation of that bilinear form for this problem, which is elastostatics. So if you remember, the bilinear form was actually an integral from xi to xj, and then we have EA dwh dx duh dx. I'm just basically replacing what the bilinear form was. Is going to be equal, and that, let's put the linear form, plus WH evaluated at xj n evaluated at xj minus WH evaluated at xi, and then n, which is the actual force, if you remember, evaluated at xi. And again, these had to hold for all test functions that belong to that finite dimensional space. Okay? Well, if you notice, everything that we have here, this was our bilinear form. And everything else, right, is basically our linear form. Just to spell it out. Okay. So, because phi I and phi j are non-zero, so now I look at only those two functions that are non-zero in the element, right? So I know that because of the Kronecker delta property, at this particular element, there are only going to be two functions that I need to include. Two, right? The one for node I and the one for node j. So we have basically a function that looks like this and a function that looks like this. So if you want to draw those functions, basically you're going to have a function that looks like this, phi I, and then you're going to have a function that looks like this. And those, and only those, are the only ones that are non-zero in that element. Okay? So then my UH for this particular element can be written as phi I of x UI plus phi j of x uj. And in matrix form, we can write that as phi, which is basically a matrix. It's a not really a matrix. It's a row vector that multiplies my lowercase u, right? So basically, if you want to write out in matrix form, it would be phi I, phi j, and this is going to be multiplying ui, uj, right? We call this row vector phi, lowercase phi, right? Because, well, in the book I reserve the uppercase phi when you are really aggregating all the shape functions in your entire mesh. So when we are at the element level, I like to use lowercase quantities, okay? And so we have the same for our test function. So now I have WH is going to be equal to phi multiplied by W in matrix form, which is actually a scalar, and so it's the same as writing that as W transpose phi transpose. Okay? So whenever we plug these two, right? The idea now is I take these two expressions and then, and then I'm gonna plug them in this equation here, and then we see what we get in matrix form, right? That is the idea. And what we get when we do this is, well, I have my vector WT, and then I have again xi, xj, ei, b transpose b, and I will explain what that is. Phi transpose phi dx, and then I have my u is equal to W transpose, and I have here a big multiplication, xi, xj, phi transpose B plus, and then I have a column vector minus Ni and J, and that has to be valid for all WT, or actually W vectors of coefficients in R2, because, well, it's actually a two-dimensional vector. So all I did, if you notice, again, I took these two expressions, this represented this way and this represented that way, and I plug all that back here, and then this is the resulting expression that we have, right? Where now this B here is our so-called strain displacement matrix, which is the one that is relating, as the name suggests, strains to displacements, right? And it's just simply the derivative. So my strain displacement matrix B is simply the derivative of my shake function vector with respect to x. And as I said, this is called the strain displacement matrix. And that is, of course, ubiquitous in everything that we do in finite elements. You're going to see this matrix popping up a lot, and it's simply basically the derivative of the shake functions in some form or another. Okay.
Are we looking at a dot product in the expression above? Because
Sorry.
are we looking at a dot product? So a W transpose, is that that's a row vector, right?
Yeah. So this essentially becomes an outer product, and so it's forming a matrix, if you notice, right? The same as this. That's why I wanted to express the test function this way, because that test function is essentially a scalar, right? But eventually, the idea is that we come up, and the Galerkin projection allows us to do that, to come up with a matrix out of all those expressions. Yeah.
The trial solution is also scalar then, right?
Yeah. It's a scalar field. So these two are scalar, and everything we do now in a 1D problem, you will see whenever we go to 2D, it's pretty much essentially the same. You will see this, and we're gonna go very, very carefully when we do 2D and 3D. But aside some subtleties, it's basically going to be the same thing. The core is here. Okay. So let me then go back to the same thing. Now I'm saying, well, this expression here has to be valid for all two-dimensional vectors, right? So again, in order for that to happen, if I don't want to have the trivial solution of having W equal to 0, 0, right? Then whatever I have inside those brackets has to be equal to 0. The same idea, right? And so we can write that expression, finally saying, well, in order for my function to be, my equation to be satisfied, then this thing inside notice when I put a lower bar, that means that I'm dealing either with a vector or a matrix already, right? Everything else is going to be scalar. That has to be equal to yeah. And well, at the element level, remember, this is equilibrium of one element, right? So we call this whole thing lowercase k. Lowercase again because we're at the element level, and that is our what? Stiffness matrix. And all of this here we call lowercase f, which is our force vector. Well, let's make then ke, because we are at the eth element. And now we have a very, very simple equation of equilibrium at the element level. This equation describes equilibrium of one single element that we can write simply as ke u is equal to fe. Okay? Well, and as we normally do in finite element analysis, we assemble the contribution of all these little pieces, right, into a unique big system that is our global system of equilibrium, right? And so to that, we normally use the so-called assembly operator, which is basically a name that is saying, okay, this is just a fancy sum of terms. So you make sure that the elements of these local matrices and vectors basically add up together in the right locations in the stiffness matrix that are dictated by the corresponding degrees of freedom, right? So now the behavior of the entire bar is obtained by considering the contribution of all elements. And so this is actually a process we call assembly. And we denote it like this. So now I'm going to say that my big matrix K, my uppercase K, which is the global stiffness matrix, is simply going to be the result of some sort of operator that we call the assembly operator. And then I say E is equal to 1 to the number of elements in the mesh. And then I'm going to have the lowercase ke, right? And the same with the force vector. My global force vector is going to be the result of an assembly procedure. E is equal to 1 to the number of elements in the mesh. And I'm going to have my lowercase fe, which is my lowercase or local force vector array, right? And so we say indeed that this A is the so-called assembly operator. Yeah, and then K and F are the global stiffness matrix and global force vector. Okay, and then again the same thing, we end up in a system of equations. Ku equals F, where we solve for U. And now U is my global degree of freedom vector that is also called, in this particular setting, global displacement vector. They are the same, and again, they are the same because of this Kronecker delta property, where remember that each coefficient in this vector physically represents the displacement. So in this particular case, and in this case only, the global degree of freedom vector and the global displacement vector are the same. And that does not happen in other formulations, right? You will see that whenever we go to PFAM, right, we lose this property because now we're going to have high order shake functions, right? And those are going to be associated with high order or generalized degrees of freedom. And then in order to get the displacement at some point along your domain, you're going to have to evaluate the full expression to determine the displacement, right? But we will get that later. Questions?
Yeah, but why, I do understand that when you go to the P version of Finite, the shape function will change in degree and might satisfy the partition of unity either faster or slower. But doesn't it then mean that like the partition of unity is still satisfied? So technically the
Where? In PFAM?
in PFAM, right?
In PFAM, we no longer have a partition of unity. So as you will see later, but of course we will get that later, okay? But the main idea is that in the PFAM implementations that we will see, you keep the linear shake functions, these ones that we are using, and then we hierarchically improve with higher order polynomials. The moment we do that, well, this we know already satisfy the partition of unity. So if we add something on top, then we lose the partition of unity property. Yeah, but questions related to this? It's kind of clear how do we get to the discrete equations, right? We did it in two different ways, like the mathematical way, which is very simply looking at the abstract form and plugging in the expressions, and then we did it from a different way, like more let's say more mechanics oriented, saying that, well, if you have equilibrium of a single bar, right, And then you obtain that contribution from all the elements in the mesh, then this is the way we obtain in a different way our system of equilibrium equations. Of course, both are equivalent. Now, can we solve this problem?
No, until you apply the boundary conditions.
Yes, we need to apply boundary conditions. So far, this matrix that we have here, right, it's singular. We have not prescribed any boundary conditions. So if we were talking about a pure Newman problem, remember pure Newman problem means there is no prescribed Dirichlet boundary condition, then you can solve the problem up to a constant, right? You have an infinite number of solutions, then, well, let's pick one solution, and then we can still get the state of stress in the bar, right? But if we have a prescribed Dirichlet boundary condition, that is not shown here yet. That basically means that we're going to have to do something to this system to remove the rank deficiency, to make sure that our system is no longer singular so that we can actually solve for you, okay? Okay, let me stop here with this lecture, and we are going to look at isoparametric formulations in the next one. And we take a little break. See you in 15 minutes.